Hi, I'm Dan, a first-year undergraduate chemistry student at the University of York, and I'm here to talk to you about
space.
Well, maybe not, but space is cool, right? Over the decades, we've devised many ways to brave the stars, from the space shuttles that take us there, to the ISS that keeps us there, and the spacesuits that let us do all of this. Humans, cousins of monkeys, to walk unharmed amongst the stars. And what underpins all of this? Polymers. That's right, I'm here to talk to you about how polymers helped us make our mark amongst the stars.
Space polymers.
We're going to go on a journey, you and I. A journey from Earth to Mars. And along the way, we're going to explore the different polymers that might make this journey possible. The first thing that people likely think of when talking about space travel is the space shuttle, and for good reason. The space shuttle is the most iconic craft for space exploration and space-related science that we know of, carrying lots of payloads into and out of space. It seems like an excellent place to start. Polymers are absolutely crucial for the entry of the craft into space and the mechanical stability of the whole rocket. The towels are used for protecting the shuttle mostly during the re-entry, where the temperatures exceed 1200 degrees Celsius. However, the towels also serve as protection during the launch from atmospheric drag and the radiation in space. Two types of tiles were predominantly used, called the LRSI and the HRSI. Both of these types of tiles are made predominantly from amorphous, that means irregular, silica fibers, which are made out of SiO2 repeating units. These fibers were layered in such a way as to maximize the amount of air trapped within the tile and given strength by ceramic bonding between the fibers. The picture shown here is a HRSI tile from the space shuttle, and the inside of it is the Li 900 material developed for NASA to fulfill the above criteria. So, quartz and glass are both polymers also made out of repeating SiO2 units. So, what's the difference? The difference is crystallinity. Crystallinity, simply put, is how regular the structure of a polymer is. A more crystalline polymer has stronger electronic interactions between the chains, which stops the structure from moving. This has several effects on the polymer. It makes the polymer harder, as the chains cannot move, and more brittle, as it gives into stress due to not being able to bend. However, more importantly here, it usually makes the polymer more thermally stable, as it will take more energy to be put into the system to break the interactions holding the structure together. A great common example here would be Kevlar, a very familiar organic polymer that many of us know. In Kevlar, due to its structure as shown here, increased crystallinity also increases strength of the material, as well as giving it stability. Crystallinity can be increased in many different ways, one of which is the cold drawing method, where the polymer is literally stretched out when it makes the otherwise tangled chains stretch and align. Here, you can clearly see the difference in the regularity of the two different forms of SiO2, glass and quartz. The structure of silica fibers is more similar to that of glass than of quartz. However, the fibers used in the tiling are exceptionally pure, allowing for the maximum amount of interactions between the fibers and increasing thermal stability. The tile is approximately 90% air, and the remainder is made of silica fibers. Air acts as an excellent insulating agent due to its low thermal conductivity, and this is just further amplified by the thermal stability of the fibers themselves. An interesting fact is that due to the very high air content, the tiles feel like plastic foam and are incredibly light. As with plastic foam, however, the tiles are not very strong and cannot be used in places where mechanical stress will be high. The tiles are used for both the aforementioned HRSI and LRSI, the difference between them simply being the coating on top of the tile. So, fibrous silica. This is an unusual form of silica. Most silicon dioxide forms are large covalent lattices, similar to that of diamond, with a tetrahedral SiO4 arrangement. Fibrous silica, however, adopts a one-dimensional structure, forming long polymerized chains, making it a lot more like a traditional polymer. These long chains can then overlap and tangle with one another, leading to the amorphous arrangement. This increases thermal stability due to the increased forces between the chain. Increased overlap leads to increased bonding. A The fibrous structure allows for a very, very low density, which then leads to a lot of trapped air and a loss of thermal conductivity. Right, that's takeoff sorted. Now, we have the dangers of space itself to deal with, and, perhaps more importantly, the dangers of damage in space, with no one around for hundreds of thousands of miles. Kinda terrifying, isn't it? Well, good job we have polymers. Our trusty friends help out again with some cutting-edge research. At the forefront of everyone's concerns is the idea that something might go horribly wrong on the journey to Mars. Obviously, this cannot be allowed to happen on future colonist ships filled with hundreds of people. We have a few ways of dealing with this problem. My personal favourites are the self-healing polymers. Like something straight out of Terminator, in 2015, a team of researchers at the Department of Chemical Engineering at the University of Michigan reached a breakthrough in the area of self-healing polymers. They found a way of making a polymer sandwich with a liquid filler between the two sheets of solid plastics. This idea has been attempted before, so what's the big deal this time around? Well, the big deal is the speed at which this reaction happens. Within seconds of the rupturing happening, the reaction initiates using the oxygen in the air to seal the hole caused by the bullet, meteoroid, etc. Previous methods that did this were way too slow, and by the time the hole would be sealed, the ship would have no oxygen left. And that's bad news for the passengers. So, for a brief overview of how it works, this is an example of a free radical polymerization. This type of polymerization relies on, you guessed it, free radicals. These are unpaired electrons that are extremely reactive and desperately want to be paired. Due to this high reactivity, the reactions tend to be extremely fast. And that's exactly what we want. So, here's an example scheme of these types of reactions. The reaction has to be initiated by something, such as a peroxide, as shown here, or oxygen. Handy. Once initiated, the radicals start chain reacting, creating longer and longer and longer and longer polymers until they reach one another, the termination step. This is almost exactly what happens in the resin between the two sheets. A hole is made, exposed to oxygen. Oxygen then kickstarts the reaction, that proceeds over the course of a few seconds, if that. The chains find one another, stop growing. Here is the exact reaction scheme directly from the research paper, as well as the individual monomers found inside of the resin. As you can see, all these have either electron-rich double bonds, or weak ether bonds. And with that, along with the help of a few rocket boosters along the way, we have made it. Quite the journey, eh? From the liftoff and the thermal protection systems of the space shuttle, Terminator-style self-healing polymers that can be used on future colony ships, to the landing systems employed by the Curiosity rover. Polymers played a central role in all of these processes. With increased private ventures such as SpaceX pledging to take humans to Mars, and NASA promising to do the same, we are on the brink of a new age in human history. Now, the vastness of an alien unexplored planet awaits us, as humanity takes one more step into the final frontier, that is, the void of space.